Space has always appeared silent, but silence can be deceptive. Beneath the stillness of the night sky lies constant motion. Planets turning, stars orbiting, galaxies colliding in slow gravitational choreography. For most of human history, the solar system was imagined as a self-contained island, a stable clockwork mechanism governed by the steady pull of the sun. Yet physics has always hinted at a deeper reality. No system in the universe is truly isolated. The solar system drifts through the disk of the Milky Way at nearly 220 kilometers per second. That motion is imperceptible to daily life, but over millions of years it carries the sun through regions dense with stars, molecular clouds, and the scattered debris of planetary formation. The galaxy is not empty between stars. It is populated by ancient fragments, remnants of violent beginnings. Theoretical models of planetary formation predict chaos. When stars are born, they emerge from collapsing clouds of gas and dust. Around them forms a spinning disk, a protoplanetary nursery. Within that disk, particles collide and merge, building larger and larger bodies. Some become planets, some remain asteroids and comets, and some, through gravitational interactions with massive newborn planets, are flung outward with tremendous force. Those ejected fragments do not vanish, they become wanderers. For decades, astrophysicists calculated that interstellar space must be filled with such objects, frozen relics drifting endlessly between stars. But prediction is one thing, detection is another. Then, in 2017, confirmation arrived with the discovery of ʻOumuamua. Its hyperbolic trajectory stunned astronomers. It was not orbiting the sun, it was passing through. Its elongated shape and subtle non-gravitational acceleration ignited debate across the scientific world. Some proposed exotic natural explanations. Others, including Avi Loeb, explored more speculative possibilities. The conversation expanded beyond orbital mechanics into philosophy. 2 years later came Borisov. Unlike its predecessor, Borisov displayed a classic cometary coma and tail. It behaved in ways familiar to comet science, even if its origin lay beyond the solar system. Together, these two discoveries transformed interstellar objects from theoretical curiosities into observational reality. And then, once again, the sky delivered another signal. It was detected by ATLAS, a survey system designed to identify potentially hazardous near-Earth asteroids. Its purpose is planetary defense, scanning the heavens for threats that might one day intersect Earth's orbit. Instead of catastrophe, it found history. The object was cataloged as 3I TLAS. That single letter, I, signifies interstellar. It marks membership in a category that did not exist before 2017. The number 3 confirms a pattern rather than an anomaly. 3 separate objects on hyperbolic paths through the solar system imply something profound. Such visitors are not impossibly rare. They are simply difficult to detect. When the first orbital solutions were computed, the eccentricity exceeded 1. In celestial mechanics, eccentricity defines orbital shape. Values below 1 correspond to ellipses, bound orbits. Equal to 1 indicates a parabolic escape. Greater than 1 means hyperbolic, an open trajectory. Hyperbolic motion means excess energy. It means the object was never gravitationally bound to the sun. It arrived from beyond the solar system and will leave forever. The realization reshapes perspective. The solar system is not a closed vault, it is porous. Material enters, material exits. Over cosmic time, gravitational interactions allow exchange between stars. The implications ripple outward. If rocky bodies can traverse interstellar space, then the architecture of planetary systems is less isolated than once imagined. During the sun's infancy, it likely formed within a stellar cluster. Neighboring stars were far closer than they are today. Gravitational encounters during that crowded epoch could have exchanged debris between systems. Some distant objects in the Oort cloud may not have originated around the sun at all. Conversely, fragments from the early solar system may now wander elsewhere in the galaxy. Interstellar objects therefore represent physical connections between stars, fragments of one system passing briefly through another. They are not merely rocks, they are ambassadors of astrophysical history. As 3I TLAS approached the inner solar system, telescopes refined measurements of its brightness and motion. Light curves hinted at rotation. Spectroscopic observations sought chemical fingerprints. Each photon reflected from its surface carried encoded information about composition, water, ice, carbon chains, silicates, complex organics. Spectroscopy allows remote chemistry, transforming faint light into molecular insight. If isotopic ratios differ significantly from solar system standards, that difference could reveal formation under alternative stellar conditions. Stars vary in metallicity, the abundance of elements heavier than helium. A body formed around a star richer or poorer in heavy elements may display subtle chemical distinctions. Thus, 3I TLAS is not only a traveler, it is a laboratory. There is also the matter of time. How long has it wandered? Millions of years, hundreds of millions. Perhaps longer than complex life has existed on Earth. During its journey, it has endured cosmic radiation, interstellar dust impacts, and extreme temperature fluctuations. Its surface may be chemically altered by prolonged exposure to galactic cosmic rays, forming complex organic residues. Such processing raises deeper questions. If interstellar space contains countless rocky fragments, and if some of those fragments originate from planets that once harbored liquid water, could microbial life survive within shielded interiors? The concept of panspermia suggests that life might spread naturally through rock transfer. Extreme microbes on Earth demonstrate remarkable resilience. Encased within stone, shielded from radiation, some could potentially survive long journeys. 380LAS does not prove biological transfer, but its existence makes the mechanism plausible. Beyond biology lies philosophy. Humanity once believed Earth was the center of creation. Then the Sun became central. Later, the Sun became one star among billions in the Milky Way. Now even the solar system itself is recognized as open to exchange. Each step diminishes isolation and increases connection. The psychological shift is subtle but powerful. The stars are no longer unreachable abstractions. Material from them has arrived. The gulf between solar systems is vast, but not impassable. Nature accomplished interstellar travel long before technology attempted it. As the object sweeps around the Sun, gravitational forces accelerate it. Solar heating may awaken volatile compounds, producing faint outgassing jets. Those jets can slightly alter trajectory, providing additional clues to internal composition. Precise tracking can detect accelerations smaller than a millimeter per second squared. Modern astronomy operates at astonishing sensitivity. Eventually 380LAS will recede. Its brightness will fade. Telescopes will lose it in the darkness beyond Jupiter's orbit. It will continue outward, carrying with it a subtle gravitational deflection imparted by the Sun. Its visit will be brief on cosmic timescales, a blink in the lifetime of stars, yet the significance endures. 3 confirmed interstellar objects in less than a decade imply a galaxy teeming with wanderers. Improved surveys in coming years may detect dozens more. A new discipline is emerging, the study of extrasolar planetesimals passing through our system. This marks a transition in astronomy from passive observation of distant exoplanets to direct study of physical samples from other star systems, even if only remotely. When reflecting on such discoveries, it becomes clear that science advances not in isolation but in continuity. Each detection builds upon centuries of physics, from Newton's gravitational laws to Einstein's refinements, from early telescopic surveys to modern digital sky mapping. The equations that predicted hyperbolic visitors were written long before the first was seen. Now observation and theory align. The day 380LAS was detected, nothing dramatic occurred on Earth. Oceans did not surge. Skies did not blaze. Civilization continued undisturbed. But in the quiet realm of astrophysics, a boundary dissolved once more. The solar system is not alone. It is a crossroads in a dynamic galaxy, and drifting through that crossroads are messengers, ancient, silent, and filled with stories written in the language of physics. The language of the universe is mathematics. Before light is interpreted, before images are processed, before theories are debated, there are numbers. Numbers are impartial. Numbers are immune to excitement. Numbers do not exaggerate. When the calculations for 380LAS first appeared on computer screens, they told a story long before headlines did. Orbital eccentricity greater than 1. That single value is enough to change the narrative of an entire field of astronomy. In classical mechanics, gravity binds objects into predictable geometries. Planets trace ellipses. Comets stretch those ellipses into long dramatic arcs. Even objects escaping the solar system under gravitational influence follow parabolic limits. But when eccentricity exceeds 1, the curve opens outward into a hyperbola, a trajectory that enters once and never returns. Hyperbolic motion means excess energy. It means the object did not borrow its speed from Jupiter. It did not steal momentum from Saturn. It did not originate in the distant Oort cloud. Its velocity was written into its motion long before it encountered the Sun. In physics, energy cannot be faked. The kinetic energy measured relative to the Sun was too large to be explained by internal solar system dynamics. No plausible gravitational slingshot could account for such speed without an earlier binding orbit. The conclusion was unavoidable. This object arrived already unbound. There is a profound elegance in that realization. The Sun, which holds 8 planets and countless smaller bodies in gravitational embrace, could not claim this traveler as its own. When plotting the inbound trajectory backward through space, the line extends beyond the heliosphere, beyond the gravitational influence of the giant planets, beyond the distant icy shell of the Oort cloud, and into the vast interstellar medium. That backward extension is not merely a line on a graph. It is a thread connecting one star system to another. The precision required to make such a determination is extraordinary. Modern telescopes record positional data with arcsecond accuracy. Multiple observations over consecutive nights refine the orbital solution. With each new data point, uncertainty shrinks. probability distributions tighten, the hyperbolic nature of the orbit becomes undeniable. In earlier centuries, such an object would have passed unnoticed. Even a century ago, detection would have been unlikely. Only in the modern era, with automated sky surveys, digital imaging, and rapid computational modeling, can faint, fast-moving bodies be recognized in time. The mathematics also reveals something deeper. The object was not simply drifting aimlessly. Its velocity relative to the Sun contains information about its galactic origin. Every star in the galaxy moves along its own orbit around the galactic center. When an interstellar object is ejected from its home system, it inherits the motion of its parent star plus whatever additional velocity the ejection mechanism provides. Thus, embedded within the trajectory of 3 ʻOumuamua is a fossil record of stellar dynamics. By subtracting the Sun's motion around the galaxy, astrophysicists can estimate the object's motion relative to the local standard of rest. If that motion aligns with known stellar streams or clusters, it may hint at a region of origin. This is cosmic forensics. The uncertainty remains significant. The galaxy is vast, and tracing backward millions of years introduces gravitational perturbations from passing stars and molecular clouds. Nevertheless, the principle stands: motion is memory. Every equation describing the object's path encodes its past. There is another quantity of interest: inclination. The angle between the object's trajectory and the plane of the solar system determines how deeply it cuts through the planetary disk. A steep inclination suggests an origin uncorrelated with the flattened structure of our planetary arrangement. And indeed, the path was not aligned with the ecliptic. It pierced the solar system from an unexpected angle, further reinforcing its foreign nature. Speed alone does not define significance. It is the combination of speed, angle, and energy that transforms anomaly into confirmation. Hyperbolic excess velocity is particularly important. Even at infinite distance from the Sun, the object retains residual speed, a leftover imprint from its interstellar journey. That excess velocity is not erased by solar gravity. It remains as evidence that the object was never gravitationally captured. The concept of capture itself is fascinating. In theory, if an interstellar object passes close enough to a massive planet, while losing sufficient energy through gravitational interaction, it could become bound to the solar system. Such events are rare but not impossible. If capture were common, the solar system might contain relics from distant stars, permanent immigrants from the galaxy. But 3 ʻOumuamua was not captured. It followed a transient path, curving around the Sun and heading outward again, destined to rejoin the interstellar darkness. The Sun's gravity bends the trajectory, increasing its speed as it approaches perihelion, the closest point to the Sun, then releasing it once more. This gravitational acceleration provides an opportunity for observation. As the object nears the Sun, heating increases, ices may sublimate, a coma may form, spectroscopic signals strengthen. If volatile materials are present, jets of gas can produce slight deviations from purely gravitational motion. Such non-gravitational accelerations were observed in earlier interstellar objects and sparked intense theoretical work. For 3 ʻOumuamua, careful monitoring of any subtle deviation from predicted gravitational paths could reveal internal composition. The mathematics of these deviations requires exquisite precision. Tiny accelerations, sometimes measured in fractions of a millimeter per second squared, can alter long-term trajectory predictions. Such minute forces are detectable only through repeated, consistent observation. In this sense, astronomy has become an exercise in patience and cumulative refinement. Each observation is a pixel. Together they form clarity. There is also the matter of brightness variation. As the object rotates, reflected sunlight fluctuates. The amplitude of that fluctuation can reveal shape. A highly elongated body produces dramatic brightness swings. A more spherical body yields modest variation. The rotation period can be inferred from periodic light curves. Rotation reveals internal cohesion. If rotation is too rapid, centrifugal force could overcome structural integrity unless internal strength exists. Rubble pile structures behave differently from monolithic fragments. Thus, light curves indirectly probe mechanical properties. Thermal modeling adds another layer. As the object absorbs sunlight, it re-emits infrared radiation. The thermal inertia, how quickly it heats and cools, indicates surface composition and porosity. A dusty, insulating surface behaves differently from exposed ice. All of these parameters converge toward a portrait of something that formed under different stellar conditions. In the early stages of a star's life, protoplanetary disks swirl with gas and dust. Within those disks, microscopic grains collide and stick, gradually forming planetesimals. Giant planets carve gaps. Gravitational instabilities scatter smaller bodies outward. Some are hurled into distant reservoirs analogous to our Oort cloud. Others are ejected entirely. Ejection requires energy transfer. When a massive planet interacts gravitationally with a smaller body, conservation of momentum dictates that one object gains energy while the other loses a negligible fraction. the small body can be accelerated beyond escape velocity, leaving its home system forever. This is not a rare accident, it is an expected byproduct of planetary formation. Thus, interstellar space may be populated by an almost unimaginable number of frozen remnants, silent witnesses to planetary chaos. For centuries, these wanderers remained theoretical. The probability of detection seems small because of their faintness and speed, yet technological progress has altered the odds. Wide-field surveys scan the sky nightly. Automated software identifies moving objects. Rapid communication between observatories allows coordinated tracking. The discovery of 3 IVITS demonstrates that theoretical predictions have crossed into observational reality. There is humility in that transition. Physics often predicts phenomena long before instruments can confirm them. Black holes were solutions to Einstein's equations decades before observational evidence accumulated. Gravitational waves were predicted in 1916 but detected a century later. Interstellar objects were anticipated by celestial mechanics well before the first confirmation. Each confirmation reinforces confidence in the mathematical structure underlying physical law. Still, numbers alone do not convey wonder. What evokes awe is the realization that this object has traversed environments beyond imagination. It has passed through interstellar clouds, perhaps through regions illuminated by distant supernovae. Cosmic rays have bombarded its surface for eons, altering chemical bonds. Micrometeoroid impacts have scarred it. Temperature extremes have cycled across its surface countless times. It is a relic not only of another star system, but of galactic history. The Sun is approximately 4.6 billion years old. The galaxy itself is more than 13 billion years old. An object wandering between stars could have originated early in the Milky Way's history. If its parent star has long since evolved or even died, this fragment may outlive its birthplace. Such thoughts stretch the imagination. In the equations describing hyperbolic motion, there is an implicit statement: boundaries are permeable. The solar system does not exist in isolation. Gravitational spheres overlap in subtle ways. Over millions of years, stellar neighborhoods shift. The Sun itself was born in a stellar cluster surrounded by sibling stars. Some of those siblings may now be far across the galaxy. During the early crowded epoch, gravitational interactions between nearby young stars could have exchanged material. It is conceivable that some rocks in the distant Oort cloud originated around another star. Likewise, material from the young solar system may have been ejected and now wanders elsewhere in the galaxy. In this sense, interstellar objects are ambassadors without intention. They carry chemistry across cosmic distances. The mathematics of 3.8 confirms that such exchange is not hypothetical, it is ongoing. When the object finally exits the solar system, it will carry with it a subtle imprint of solar radiation and gravitational deflection. Its path will have been altered slightly by the encounter. That alteration, though tiny, becomes part of its future history. If it eventually passes near another star, that star's gravity will bend its path again. Over billions of years, cumulative deflections create a random walk across the galaxy. Somewhere in the distant future, another civilization, perhaps orbiting another star, may detect it. Their astronomers may compute its hyperbolic orbit relative to their Sun and conclude that it came from afar. They may trace its incoming direction and discover that, millions of years earlier, it passed near a yellow star in a minor spiral arm. That yellow star would be the Sun. Thus, the mathematics does more than describe motion. It connects epochs and civilizations that may never overlap in time. The discovery of 3.8 is therefore not merely a data point. It is a reminder that physics operates universally. The same equations governing falling apples describe the dance of stars and the trajectories of interstellar wanderers. In that universality lies a quiet unity. The numbers that first appeared on a screen, eccentricity greater than 1, represent more than a curve. They represent evidence that the cosmos is dynamic, interconnected, and far more fluid than once believed. And the mathematics, calm and uncompromising, has once again revealed a deeper truth about the architecture of the universe. The memory of the first confirmed interstellar visitor still lingers in modern astronomy. When ʻOumuamua was detected in 2017, it did more than pass through the solar system. It shattered an assumption that had quietly endured for centuries. Until that moment, interstellar objects were theoretical necessities, predicted by equations but never seen. ʻOumuamua transformed prediction into reality. Its discovery was sudden, its departure was swift, but its implications were immense. The object displayed a hyperbolic trajectory, confirming that it originated beyond the Sun's gravitational influence. Yet trajectory alone was not the only surprise. The light curve suggested an extreme shape, possibly elongated like a cigar, or perhaps flattened like a pancake. Its brightness fluctuated dramatically as it rotated, indicating a geometry unlike typical asteroids. Then came the most intriguing detail: a slight non-gravitational acceleration. Comets accelerate subtly when sunlight heats their surfaces, causing volatile ices to sublimate and produce jets of gas. These jets act like tiny thrusters. But in the case of ʻOumuamua, no visible coma or tail was detected. No obvious gas emissions were observed, yet the acceleration was measurable. This anomaly ignited scientific debate. Among those who explored unconventional possibilities was A.V. Loeb, who suggested that the unusual properties warranted consideration of artificial origin. The suggestion did not assert certainty, but it challenged complacency. It asked whether assumptions about natural formation were being applied too rigidly. The broader scientific community responded with alternative natural explanations: hydrogen icebergs, nitrogen fragments from exoplanetary surfaces, highly porous cometary bodies. Each hypothesis attempted to reconcile the data without invoking technology. Debate is not weakness in science, it is strength. Competing models sharpen understanding. 2 years later, in 2019, a second visitor arrived at Borisov. Unlike ʻOumuamua, Borisov behaved almost reassuringly normal. It displayed a visible coma. Spectroscopy revealed familiar molecules such as cyanide and water vapor. It looked and acted like a comet, except its orbit was unmistakably interstellar. Borisov confirmed that ʻOumuamua was not an observational fluke. Now, with the detection of 3I TLAS, a pattern begins to emerge. 3 objects within less than a decade suggest that the galaxy is not sparsely populated with wanderers. Instead, detection capability may have reached the threshold necessary to reveal what has always been present. Each interstellar object represents a different chapter in a larger cosmic narrative. ʻOumuamua raised questions about morphology and acceleration. Borisov reinforced expectations about cometary composition. 3I TLAS now extends the dataset, allowing comparative analysis. In astrophysics, sample size matters. With only one object, anomaly dominates discussion. With 2, classification begins. With 3, statistical reasoning becomes possible. The study of interstellar objects is evolving from curiosity into discipline. One of the profound realizations emerging from these discoveries is that planetary systems are not isolated laboratories. During formation, gravitational chaos is inevitable. Giant planets migrate inward and outward. Resonances amplify orbital instability. Smaller bodies are scattered violently. In the solar system's early history, Jupiter likely played a decisive role in ejecting countless planetesimals. Computer simulations indicate that trillions of icy fragments may have been flung into interstellar space during the Sun's youth. If this occurred here, it must have occurred elsewhere. Multiply that process across the hundreds of billions of stars in the Milky Way, and the implication becomes staggering. Interstellar space may contain an ocean of debris, perhaps quadrillions upon quadrillions of frozen fragments. Most remain undetected because of distance and faintness. Only those that pass relatively close to the Sun become visible against the stellar background. The detection systems responsible for identifying such objects are themselves marvels of engineering. Surveys like ADIOS scan large portions of the sky nightly, searching for transient motion. Sophisticated software filters out known asteroids, artificial satellites, and noise artifacts. What remains are candidates requiring further observation. When 3I TLAS appeared in survey data, its motion against the background stars stood out. Its path was not aligned with the ecliptic plane, the flat disk defined by planetary orbits. Instead, it entered at an inclination inconsistent with local origin. Backtracking its trajectory mathematically extends its path beyond the heliosphere, the bubble of solar wind marking the outer boundary of the Sun's influence. Beyond that lies interstellar space filled with diffuse gas, cosmic rays, and magnetic fields. That region is not truly empty. It is a medium shaped by supernova explosions and stellar winds. Objects traveling through it accumulate subtle changes. Cosmic radiation alters surface chemistry. Impacts micrometeoroids create microscopic craters. Over millions of years, these effects accumulate. By studying the reflectivity and spectral characteristics of 3I TLAS, astronomers attempt to infer its exposure history. A reddened surface may indicate prolonged cosmic ray processing. Volatile depletion could signal repeated heating cycles near other stars before ejection. Each observation adds context. There is also the possibility of structural diversity. ʻOumuamua's unusual light curve suggested extreme elongation or flattening. Borisov appeared more typical. If 3I TLAS exhibits yet another morphology, it would reinforce the idea that interstellar objects represent a diverse population, reflecting varied formation environments. Planetary systems differ significantly in architecture. Some possess hot Jupiters orbiting extremely close to their stars. Others host multiple gas giants in wide orbits. Stellar metallicity influences dust content and planet formation efficiency. Binary star systems introduce additional gravitational complexity. Therefore, debris ejected from those systems should display wide variation in composition and structure. Interstellar objects may eventually provide indirect sampling of exoplanetary diversity. The implications extend further. In astrobiology, the possibility of panspermia, the transfer of life between star systems, has often been considered speculative. Yet the existence of physical carriers makes the mechanism conceivable. Microorganisms embedded deep within rock could be shielded from radiation. Laboratory experiments demonstrate that certain extremophiles survive vacuum and intense radiation for extended periods. The journey between stars, however, could last millions of years. Survival over such timescales remains uncertain. Still, the presence of interstellar rocks demonstrates that transport is not impossible. The philosophical consequences are subtle but transformative. Life, if it exists elsewhere, may not be entirely isolated. The galaxy could function as a vast ecological network, exchanging material over astronomical time. Even without biology, the exchange of organic molecules alone has significance. Complex carbon compounds form in interstellar clouds and protoplanetary disks. If such molecules are distributed widely through ejected debris, prebiotic chemistry could be seeded across multiple systems. 3i therefore represents more than a moving point of light. It embodies a process that links stellar evolution, planetary formation, chemistry, and potentially biology. When considering these ideas, perspective shifts. Humanity often views itself as standing at the center of observation, gazing outward at distant stars. But interstellar objects reverse that relationship. They are emissaries from elsewhere, arriving uninvited yet profoundly informative. They remind that cosmic evolution is not compartmentalized, it is continuous and interconnected. The Sun itself is not stationary. As it orbits the galactic center, it passes through spiral arms rich with star formation. Over hundreds of millions of years, close stellar encounters are statistically inevitable. Each encounter perturbs distant comet reservoirs. Some objects are nudged inward, others are flung outward. Thus, the traffic of interstellar debris is bidirectional. In the distant future, 3i will depart permanently. Its path, slightly altered by solar gravity, will carry it into new regions of the galaxy. It may pass near other stars, perhaps even entering their planetary zones before continuing onward. From a cosmic perspective, its journey is ongoing. From a human perspective, its visit is brief but monumental. With each new interstellar detection, a subtle boundary dissolves. The solar system transitions from isolated system to participant in galactic exchange. 3 visitors in less than a decade imply that detection rates will increase as instruments improve. Future observatories may even attempt interception missions. Spacecraft launched to rendezvous with incoming interstellar objects, capturing direct samples. Such missions would mark a new era in exploration, not traveling to distant stars, but allowing fragments of distant stars to come here. In that vision lies a profound shift in strategy. Rather than sending probes across light years, humanity can study pieces of other systems that naturally arrive. The cosmos has begun delivering samples. And with each arrival, the narrative expands from anomaly to confirmation to emerging science. 3i stands as the next chapter in that unfolding story. The discovery of 3i was not the result of chance observation by a lone astronomer peering through an eyepiece. It was the outcome of a planetary, scale vigilance system, a technological extension of human awareness scanning the sky every clear night. That system is 8LS. ALAS was not built to search for interstellar visitors. It was designed for survival. Throughout Earth's history, impacts have shaped biological evolution. 66 million years ago, a large asteroid struck near present-day Mexico, contributing to the extinction of the dinosaurs. That event permanently altered the trajectory of life on this planet. The lesson is sobering. Celestial mechanics is not merely abstract mathematics. It can intersect directly with biology. Modern civilization, armed with technology, has resolved to ensure that no such surprise goes unnoticed. ALAS scans vast portions of the sky repeatedly, identifying faint moving objects that might approach Earth. Automated algorithms compare sequential images, detecting motion against the fixed stellar background. Most detections are routine, known asteroids, distant comets, harmless fragments. But occasionally, something unusual appears. When 3i was first recorded, its motion was too rapid and its path too steep to be easily categorized. Initial orbital fits revealed a trajectory inconsistent with near-Earth objects. Follow-up observations from other observatories refined the data. The eccentricity was calculated. It exceeded 1. In that moment, the purpose of the system transcended planetary defense. It became a gateway to galactic archaeology. The irony is elegant. A system built to protect Earth from destruction uncovered evidence of cosmic connection. The architecture of ALAS reflects a broader transformation in astronomy. For centuries, astronomical discovery depended on manual observation. The telescope was an extension of human sight. Today, telescopes are robotic, digital, and interconnected. They generate torrents of data nightly. Artificial intelligence assists in pattern recognition. Discovery has become computational. This transformation allows detection of transient phenomena, supernovae, gamma-ray bursts, near-Earth asteroids, and now interstellar objects that would have been invisible to earlier generations. The detection of 3 interstellar objects within a decade suggests that the galaxy may be permeated by such wanderers. Statistical models estimate that at any given moment, multiple interstellar objects may reside within the outer solar system. Most are too small or faint to detect. Only when one passes relatively close to the Sun does it brighten sufficiently for observation. This raises a profound question. How many such visitors have passed unnoticed throughout Earth's history? Before modern sky surveys, detection required fortunate timing and exceptional brightness. It is entirely plausible that countless interstellar objects have traversed the solar system undetected over billions of years. Some may have passed close to Earth's orbit. A few may even have impacted the early Earth. If so, material from other star systems could already be embedded within terrestrial geology. The possibility expands imagination. As 3i Hellas approached perihelion, its closest approach to the Sun, solar radiation intensified. If volatile compounds exist beneath its surface, heating would trigger sublimation. Gas jets might form, producing a faint coma. Such activity would classify the object as cometary in behavior, even if its origin lies elsewhere. Spectroscopic instruments around the world turn toward it. By dispersing reflected sunlight into a spectrum, astronomers searched for absorption lines corresponding to specific molecules. Water, carbon monoxide, methane, ammonia, each leaves a signature. The composition matters profoundly. If the chemical fingerprint closely resembles that of solar system comets, it suggests that planetary formation processes are broadly universal. If unusual compounds or isotopic ratios appear, it may reveal diversity in stellar chemistry. Stars differ in metallicity, the proportion of elements heavier than helium. A star formed early in the galaxy's history may have lower metallicity than the Sun. A star formed in a region enriched by previous supernovae may contain higher abundances of heavy elements. These differences influence the composition of surrounding planetesimals. Thus, by studying 3i Hellas, astronomers are indirectly studying another star. There is also the matter of rotation. Variations in brightness over time can reveal rotational period. A rapid rotation may indicate structural integrity. A slower, tumbling rotation could imply a rubble pile structure loosely held together by gravity. Each scenario provides clues to its formation and ejection history. Ejection itself requires gravitational violence. In young planetary systems, massive gas giants dominate. When a small body approaches such a giant planet, gravitational interactions can transfer energy efficiently. The smaller body may gain velocity sufficient to escape the star entirely. This process is not rare. Simulations of early solar system dynamics suggest that Jupiter alone may have ejected enormous quantities of debris. Multiply that mechanism across the hundreds of billions of stars in the Milky Way, and the scale becomes staggering. Interstellar space may be filled with remnants of planetary birth pangs. The idea reframes emptiness. The void between stars is not truly void, it is a sparse sea of frozen fragments. Each interstellar object, including 3i Hellas, represents a data point in that ocean. With only 3 confirmed examples, 100 ʻOumuamua, 2i Borisov, and now 3i ATLS, patterns are only beginning to emerge, yet even 3 is transformative. The progression from 1 to 3 shifts perception from anomaly to population. Future observatories, such as next-generation wide-field telescopes, will dramatically increase detection sensitivity. Objects smaller and fainter than current thresholds will become visible. Detection rates may rise from rare to routine. When that occurs, interstellar objects will no longer be headline events. They will be cataloged as naturally as near-Earth asteroids are today. But at this stage, each detection carries philosophical weight. There is something profound about recognizing that physical material from another star system has entered our own. Exoplanets, though thousands have been discovered, remain distant points of light inferred through indirect measurement. Interstellar objects are tangible, even if only observed remotely. They are pieces of other systems physically passing through ours. The concept alters cosmic perspective. For centuries, humanity wondered whether the stars are isolated lanterns scattered across an empty void. Now it is clear that material exchange occurs. Over millions of years, gravitational interactions mix debris subtly but persistently. The solar system is not a closed museum, it is part of a galactic ecosystem. As 3i Hellas continues its journey outward, its brightness will diminish. Eventually, even the most powerful telescopes will lose track of it. Its data will remain, orbital parameters, spectral signatures, rotational characteristics, archived in scientific literature. But the object itself will move on, re-entering the cold darkness between stars. It may wander for millions of years before encountering another stellar system. It may never approach another star closely. Or it may one day pass near a distant world where astronomers observe its hyperbolic arc and reach conclusions similar to ours. In that distant epoch, its brief encounter with the Sun will be just one episode in an endless journey. There is poetic symmetry in that thought. The system designed to shield Earth from cosmic threat has revealed instead cosmic continuity. ATLAS scanning for danger uncovered connection. The sky, once viewed as static backdrop, is revealed as dynamic thoroughfare. The discovery of 3i ATLAS reinforces a truth that physics has long implied the universe is not compartmentalized. It is interconnected through gravity, motion, and time, and sometimes in the quiet stream of observational data, that interconnectedness announces itself as a faint streak of light crossing the stars. Beyond trajectory and velocity lies a deeper question: origin. Every interstellar object is a survivor of catastrophe. Planetary systems are not born in serenity, they are forged in turbulence. In the earliest epochs of stellar formation, protoplanetary disks churn with gas, dust, and growing planetary embryos. Gravitational interactions amplify instability. Massive planets migrate through the disk, scattering smaller bodies like cosmic shrapnel. Within such chaos, countless fragments are accelerated beyond escape velocity. When escape occurs, gravity releases its hold permanently. The fragment becomes an exile, no longer bound to its parent star, yet forever carrying its chemical memory. 3i ATLAS must have experienced such an event. Somewhere long ago, around a distant star whose light may never be identified, gravitational forces flung this object outward with sufficient energy to sever its bond. That severing is violent. Orbital resonance with a giant planet can gradually pump eccentricity until close encounters occur. In a single gravitational interaction, energy transfer can catapult a small body into interstellar space. The giant planet loses negligible momentum, the small body gains freedom. This mechanism likely occurred trillions of times across the Milky Way. Thus, 3i ATLAS is not extraordinary in its ejection. What is extraordinary is detection. Once expelled, the journey becomes one of endurance. Interstellar space is cold, only a few degrees above absolute zero. It is permeated by cosmic rays, high-energy particles accelerated by supernova remnants and magnetic turbulence. Over millions of years, cosmic radiation alters surface chemistry, breaking molecular bonds and creating complex organic residues. This process, known as space weathering, gradually darkens and reddens exposed surfaces. Spectroscopic signatures shift subtly. By analyzing reflected light, astronomers attempt to infer the degree of cosmic exposure. If 3i ATLAS displays a heavily processed surface, it may indicate immense age in interstellar transit. If fresher ices are detected, perhaps its journey has been shorter. Time leaves fingerprints even on stone. There is also the possibility of internal preservation. Beneath an irradiated crust, pristine material may remain unchanged since formation. Such material could encode information about the protoplanetary disk from which it emerged, temperature gradients, chemical abundances, isotopic ratios. Isotopes are particularly revealing. Variations in oxygen or carbon isotopic ratios can indicate stellar nucleosynthesis environments. Stars produce elements through fusion and distribute them via stellar winds and supernova explosions. The abundance pattern of heavy elements in a given star reflects its generational history within the galaxy. Therefore, a fragment born around a star with slightly different metallicity than the Sun may carry isotopic distinctions measurable from afar. Each photon reflected from 3i ATLAS carries that encoded history. There is another profound implication. If rocky bodies are ejected frequently from planetary systems, then the galaxy is not only exchanging inert material, but potentially exchanging the ingredients for life. Complex organic molecules, amino acid precursors, carbon chains, polycyclic aromatic hydrocarbons, form readily in interstellar environments and protoplanetary disks. If such molecules survive ejection and transit, they become seeds drifting between stars. The theory of panspermia proposes that life, or at least its molecular precursors, could be distributed in this way. The concept does not require intent or design, it requires only physics. Impacts can eject material from planetary surfaces. Shielded within rock, microbes might survive. Over immense timescales, that rock may encounter another planetary system. Whether survival over millions of years is feasible remains uncertain. Yet the mechanism for transport is now undeniable. The existence of 3i ATLAS demonstrates that nature performs interstellar exchange without propulsion systems, without engineering driven solely by gravity and time. As 3i ATLAS curves around the Sun and begins its outward trajectory, it acquires a subtle alteration in path. The Sun's gravity bends its motion. That deflection becomes part of its history. When it departs, it will carry a memory of this encounter encoded in its velocity vector. In the distant future, if it passes near another star, that star's astronomers, should any exist, may detect its hyperbolic approach. They may calculate its incoming direction and deduce that millions of years earlier, it passed near a yellow dwarf star in a minor spiral arm. In that moment, the Sun becomes part of its story. This reciprocity reveals a cosmic symmetry. Just as 3i ATLAS brings with it the history of another system, it will carry away a fragment of ours. The solar system, once imagined as isolated, is better understood as a participant in a galactic network of gravitational exchange. The detection of 3 confirmed interstellar objects, 1 ʻOumuamua, 2 Borisov, and now 3 ejected, suggests that the threshold of awareness has been crossed. Instruments have become sensitive enough to reveal what has always been true: the boundaries between stars are permeable. Future observatories will likely detect many more. Statistical analysis will refine estimates of their abundance. Missions may be conceived to intercept future arrivals, capturing samples directly. Such a mission would represent a new era of exploration, studying extrasolar material without traveling light years. Until then, observation remains the primary tool. Light curves, spectra, orbital mechanics, these are the instruments of cosmic archaeology. There is humility in recognizing that rocks have achieved what civilizations aspire to accomplish. They have traveled between stars. Yet there is also empowerment. Understanding the physics that governs their motion equips humanity with the same knowledge required to attempt similar journeys deliberately. The day 3 ʻItalas was detected did not alter Earth's orbit. It did not shake continents or darken skies, but it quietly expanded the map of understanding. The universe is not divided into isolated compartments of matter and meaning. It is a continuum of motion, governed by gravity, shaped by time, and interconnected across unimaginable distances. And drifting through that continuum are ancient messengers, silent fragments of distant suns, reminding that even in the vastness of space, nothing is truly alone.